As the built environment faces growing pressure to reduce its environmental impact, architecture is shifting from designing for appearance alone to designing for measurable performance. Today, decisions about building form, facade, orientation, and materiality are increasingly informed by data, simulation, and computational analysis, making buildings more energy efficient. In today's episode of Friday Frame, computational design expert Anurag Biswas explores the theme Form Follows Performance, talking about how computational tools can be used to analyze environmental performance and optimize the design decisions from the initial stages of a project.
Building is a machine for living in. Le Corbusier has said that. But if we compare with the other machines, suppose for car, the production facilities, the whole workflow is much more optimized so that in minimum cost you get maximum output. But in architecture, engineering, and construction, that is the AEC industry, uh, we have been very slow to adopt all the processes and all the automation. But slowly the things are taking up, and also we are trying to uh, optimize different performance of the building. So let's not talk about facade. Facade is a very important component or important part of that machine that we call building. So what is the use of that? Why is it important? Because it gives us protection from the outside. It makes us comfortable inside, and also it acts as an interaction between the inside and the outside. And also it's the face of the building. We know a building by its facade. And what are the performance criteria for facade? So there are different criteria that we can tell. So we have structural performance, we have the look and feel, the aesthetics, we have the constructability, how the facade is fabricated and constructed and put joined together in the building, and also the environmental performance. So out of this performance criteria, we come to some design decisions. And with that design decisions, our high performance buildings are uh, designed and constructed. In all the areas, like in structural performance, and look, feel, and constructability, and environmental performance, today computational design has been being used. Uh, for me, I have worked in I've never worked with the structural performance. The structural engineers do that. I've worked with the other three components, but where I have expertise is in environmental performance, and I will talk about that in our session. So, what are the environmental performance objectives? The objectives are that we have to ensure comfort. That comfort could be thermal comfort or daylight comfort. And also we have to ensure energy efficiency. Energy efficiency at today's world is very important because for a number of factors, our buildings constitute around a rate in some study like 35 to 40% of the energy consumption of a nation. And if you see about India, the trade deficit is mostly about energy deficit. India buys a lot of energy from outside, lot of oil from outside. So India is very energy deficit country. So in Indian condition, energy efficiency for buildings is very important. And we also need to reduce the environmental impact. We need to reduce the CO2 GHG emissions. So these are the objectives. Now let's go to different criteria. So we'll try to describe different criteria on which we evaluate the performance of the facade. So first is daylight quality. Uh, Daylight quality is very important. Now a lot of studies have come up that shows that if in a room you have adequate daylight, your mood is elevated, your mental health and well-being is much better. And also if you have daylight and you are not using your artificial light, then it is also reducing your lighting loads. So in that way it is reducing the energy consumption, and also it is uh, it is also contributing to the well-being and the mental health of the occupants. We need to ensure that when we are working in our work plane, we have adequate daylight. So like for in our office, we have 300 lux as the performance criteria. We also need to ensure that there is no glare or overexposure. So what is glare? In simple terms, glare is when there is drastic change between two adjacent light sources. So let me give you an example. So suppose you're in a traffic and a lot of cars are coming there. So they have headlights, right? But because in that traffic in a city, in an urban center, there you have lights all around. So those light doesn't is not bad for your eyes. So you can still see it. But suppose you are in a lonely, dark road and suddenly one car comes and its headlight would blind you. Why so? Because out of all the darkness, suddenly we have one light source which has very much high illumination level. So that's why we need to reduce the glare. So in a building, suppose we have enough illumination, but there is a drastic difference between 2 point sources, then even if the illumination level is adequate, we won't be able to see it. The glare would blind us. So we also need to take care of that. So I'm giving you some examples. How do we do? So here we have one example. So see here we have this example. This is our base case. Here we do not have any light shelf. So here there are two metrics that are being calculated. We have spatial daylight quality, SDA, and annual sunlight exposure. So spatial daylight quality is a metrics for your annual illumination level. I'm not going too much into detail of this metrics, but this is how this tells you about your quality of the illumination. And this annual sunlight exposure, this gives an idea of glare. This is not your glare exactly, but it gives you an idea about will there be a glare or overexposure to the sun. So these metrics are now taken by LEED, and if you're doing LEED certifications, you have to meet this metrics. So here in this example, we do not have light shelf, and so you can see that our SDA levels are 28.1%, and our AAC, that is sunlight exposure, are much bigger, like 31.3. Then when you give one light shelf, your SDA level, your illumination level increases, but your glare is reduced. So that's how just with one light shelf, we can make our buildings much more efficient in terms of daylight quality. So another example. So here we have different examples of sunlight, skylight. So skylight, we have different options, and out of that, the designer can choose which would be best for his design. Then we have another example where there are different kinds of facade patterns, and these are design criteria evaluations. We have UDI value, that is another metrics, useful daylight illuminance. And from here, we can compare and know which of the options are performing better. There is another example, another example. Here we have two kinds of facade and two kinds of glare. So as you can see, so we have this much difference. So in this way, we can understand what is the glare performance of our building. So we have this daylight glare probability. This is has a short term called DGP. DGP values tells what is your glare. Then we come to view to the outside. View to the outside is also very important because a number of research that is going on now recently, many more research are going with CMU and Berkeley, which tells the which are researching on the psychology of human beings when they have view to the outside. When through their windows they can see outside, and that by intuition we already know that it actually helps us. It's good for our well-being. So view to the outside is also important. If you talk about your real estate for office spaces, if you have view to the outside, the prices goes up in that way. So we have two options, like without box for 3 orientation and with box window for 3 orientation. So here you can see with box window, our view to the outside is much less. So these are just examples. In real life scenario, we would have a little bit more complicated scenarios. And also the energy performance of the building is important. So we know energy efficiency is important. We also need to ensure thermal comfort. We need to ensure that the people who are residing in the building are comfortable enough. And if we make sure that energy load of the building is much less, that decreases our energy annual electricity bills. So each year we would be having one saving. And also because the energy load is much less, our HVAC equipment capex, that is capital expenditure, would also be less. So in here we can see one energy analysis for one shading screen openness. So this talks about the peak cooling loads. So there are different options. So different options about the horizontal shading and SHGC. So these are options, and the performance we get with this EPI. EPI is, EPI, not EPI. Here we are getting the energy loads. So through this graph, we can understand out of number of options, which option would be the best suitable for our case. So we had been doing this kind of environmental analysis for ages. We would just draw it, but the problem with this kind of analysis was it was not backed by real data. You could just shift your line little bit and maybe it would suit your design. But when it would get built, there is no provision for errors. It has to be built right the first time. So we need to make sure that our design options, our design decisions are backed by data and are evidence based. So that's why we need data to we need to collate data to inform our designs. So as you can see, this is the Tower of Shadows in Chandigarh. It was built by Le Corbusier. Before building Chandigarh, so he built this one and he studied the shadow of this building. And from that shadow, whatever the outputs he got, he used those in designing his buildings throughout Chandigarh. And also you can see that we have this vernacular architecture which has evolved through trials and errors. But for in today's case, we are building so many buildings. There is no provision for trial and errors. There are no way that we can build full-scale models. So we have we have to build some simulation and models and do some analysis to predict its performance. So we do simulation and analysis, and from there we get some accurate data, and that accurate data gives us our optimum design. So if we do it for just one option for the building, so that's quite easy, quite straightforward. But if you're doing for multiple options, because we see that there are so many performance criteria, and out of that, there could be so many design options. So if we want to take care of each and every parameters, it becomes really difficult to do it one by one. So this is one kind of analysis where 5,000 simulations were done. So we have different factors like infiltration, U factor of the window, ventilations, heat capacity. Then, this one was U factor of the wall. This one was U factor of the window. Then this is side fins. This is SHGC, reflectance, solar panels, then wind fact ratio, that is WWR, wall window ratio. And then we get our performance factors here. We have the energy and we have the daylight. So out of this, we can understand that how our which options would be good for us. But to do all the analysis one by one, to do 5,000 simulations one by one is next to impossible. So that's why we use things like automation and coding. And we use scripting languages like Python, C#, and visual programming languages like Grasshopper and Dynamo. Now, you might say that why don't we build one robust software that can do everything? But the thing is that there are so many parameters and there are so many options that there is no one simple solution. So one software cannot do. And each building, each project gives new challenges that you cannot do through a software. So that's why we have to go into computational design. That's why we use scripting languages to do this kind of analysis. So now let's talk about glass selection. So we have three major parameters of glass that we take into account. So we have this U value, we have ACJC, and we have transmissivity, transmittance of the glass. So U value tells what would be the conduction of the heat. So we would want the lower U value, lower the U value, lower the energy loads. And for ACJC, it talks about the heat gain through window. So basically we have three ways how heat transfers: radiation, convection, and conduction. So U value take care of the conduction, ACJC take care of the radiation. And now we have TVS, or the transmittance of the light. So higher the transmittance, higher the illumination level. So it talks about how much light energy would enter through the glass. So what we would want in our design is we would want to have less U value, less SHJC, but higher transmittance. But there is a problem with that. So what are the problems? The problem is the way the materials are being manufactured. If you decrease the SHJC, your transmittance also increases. So basically what SHJC does is it blocks the solar energy, and what transmittance does, it gets the light energy inside. So the glass manufacturers have to be very efficient in a way how they build the high performance glass. So glass manufacturers like Saint-Gobain, so that's why they have created some high performance glass which are though they have very low SHJC and U value, then also they have high transmittance. But as you go towards more high performance, your cost also increase. So also in our analysis, you have to take care of the cost. So when you're doing cost optimization, computational tools also become very useful. Suppose for 5,000 simulations that you are doing, you just increase one parameter of the cost of each of the glass, and then you do the simulations, and then you can understand, okay, so these would be my cost. And maybe the client or the designer, then he would see, okay, my best option would be very costly for me, but my second or my third option could be not that great, but still we can go with it. It would give us adequate performance. So in that way we can use. So after we have finalized what would be our values of the glass through different analysis and simulations, so then we select from this chart, that this chart is, I think, by Saint-Gobain only. So you'd have this chart, and here you can select which glass would go for you. So most of the times you won't get the exact one, so you would get somewhat close to that. So here, suppose this analysis we got an U value of 1.6. So I would go with 1.9, 1.8, 1.6. So all the values. So this all options I would give to the clients, and also the other stakeholders would make the final call. So it's a iterative process. So a lot of back and forth goes on in the project. So, but when you have data, it gives you a big leverage to understand how your glass and how your building would perform. So you have better options. So what is the methodology? So methodology is we need to start uh, doing this analysis as early as possible in our design. So we have different design stages. So according to the BIM uh, analogy, we have this level of detail. So in level of detail, that is the design initiation. We just then we have this concept design for LOD or level of detail 200 and so on. So and if generally sustainability experts are obtained in the later stage, but we need to start doing analysis as early as possible. So the ability to impact the project is much less when the project has advanced. So and the cost also increases. So we need to start as early as possible. So 1 minute. Uh, So yeah, so this is your ideal workflow. So you would have this baseline and target. You would have the analysis. So this tells you, okay, this would give you an idea. Okay, for facade we can uh, go for this kind of things, and weed out many other options that would be too off your goal. Then you'd have your massing and orientation. Then you'd have your envelope optimization. Then finally, you can have your system optimization. And how you do it? You do it through different simulation platforms like OpenStudio, Ladybug, Honeybee, Energy Plus. A lot of people are now into Ladybug and Honeybee, and my expertise is mostly in Ladybug and Honeybee. So it uses computational tools at the fullest, and you can do a lot of insightful analysis with Ladybug and Honeybee. These are flexible, very flexible. Uh, but Ladybug and Honeybee works with your Grasshopper. So this is also at computational tools. So I'll give you some overview of few projects. So this one was hospital. So I'll skip this initial analysis that we had done. So the first thing that we had done was form analysis. So we took the best possible form out of different options. Then when the form was finalized, then what the architects did, they designed different facades for different areas of the building. So there were like 7 or 8 options of the facade. Now for each facade options, we did optimization. So we did different kinds of optimization. So this was just one query out of like 100 queries. So this was an iterative process. So not only me, the architect, there were the structural engineers were also involved, and also the finance department from the client. So they were also involved. So it was a collaborative work. So how we came up with the different designs. So as you can see, we have this values. API values is your energy performance values, and your SDA gives your daylight quality values. So we have different values. Now see, suppose here we are not going to the least API values to 201. So this one would have been our best, but here we can see our SDA values are not that good. So that's why we have not taken it. So SDA values 70% would be good enough. So this 205 API value where we have for this option. So these options we have taken. So in this way, we can select different options. So now we'll give a study about dynamic shading. So what is dynamic shading? So the shading is mechanically, it revolves with your sun rays. So as you can see, if you have just static, so suppose this one is your static shading, so it is fixed all the time, you would have values this one as static. But if you have dynamic, so your louvers are movable, then you'd have your better performance. Your better performance, you can see that illuminance, your daylight is improved, your glare is also much less, And also your energy performance has improved. Like you can see surface radiation. For the static facade, it was this. For the dynamic facade, we have much lowered values. So the kind of problem that we have in selecting our glass that can be circumvented with this dynamic shading. Now we have different kind of electrochromic glasses also. So like sage glass is I think by Saint Gobain only. So there what happens, depending, they have some sensors uh, which takes the radiation values of the sun, and that sensors tells different electrons to go through that this surfaces, and the ACJC and uh, transmittance value of your glass changes. So these are very expensive. I don't think in India there are any projects. There might be. I don't know that. So in this way, that uh, uh, I think in future we would have much more high performance buildings. A lot of research are going on in this field. I guess sky is the limit. So I hope through my presentation, it was a very brief presentation. I have not gone deep into many of the aspects, but I hope it would give many of you guys a little bit interest of what kind of things that could happen, and maybe many of you would uh, apply that in your design or do some research regarding that. So that's all, guys. That was my time.